All right, so welcome back to another part or another section of lecture 13. In this, we will start with looking at an irregular lattice in order to calculate a variogram or a semi-variogram, calculate an experimental variogram to be more precise, right. We saw how to do it for a regular lattice in the previous part of this lecture. So, what you have on the screen here is an administrative groundwater data set that we have seen, we have worked with when we did exploratory data analysis, spatial data analysis, right. And this data, these data are an irregular lattice. That is to say that if I were to divide the domain of interest, which is the state of Uttar Pradesh, into equidistant cells that are sort of marked by rows and columns in I and j direction or x and y directions, right, of certain size, I will not have data that is going to be observed in every cell of in the entire domain, right. To see an example, we can look at any vacant space within the spatial domain of interest. Whenever we see a space that is vacant, for example, the square on the screen, this represents the region which remained unsampled in the year 1998. And that is not surprising. You cannot possibly put wells, these are wells that are going to have to be dug into the ground to a certain depth. So, you can't have at day 0 all the places being sampled, right. What is encouraging is there is quite an intensive sampling even in 1998 when these data set were first made available, right. Now, when if you sort of see what happens is, if you have a row column representation, that is data that are contained in cells in the entire region, in this cross section that we are looking at, there will be no data. And what is the consequence of that? The consequence is that if we were to sort of transport the idea of collecting this neighborhood set NH by starting from a tail and going up to a head in a strict direction as encapsulated in the definition of a spatial lag vector H, then we may not find any corresponding pairing observation from this tail, right. So, we will have a vacant observation. So, for a lot of locations, while for some locations we are going to find such pairs, there are going to be a lot of locations where we are not going to be able to find any of these pairs, right. So, what do we do then, right? And this is very important because see, most of the real world data sets are going to be similar to the one in front of our screen right now, right. In most places when people monitor air pollution levels, they are not going to be able to put these air pollution monitors in a grid, nice looking grid format, so that you have a regular lattice. You are going to encounter irregular lattices when you are working with these real world data sets. Okay. So, let us see what's the workaround. The workaround is that when you have a tail to a head lag vector that you can scan around every part of this data set, you do not make its direction very strict. You allow for the fact that you will be able to, keeping the tail fixed, you will be able to scan a little bit angular in angular direction from the strict direction H, which is let us say west to east. Not only that, you also want a possibility that maybe you do not have in the strict east west direction, you do not have any value observed at the head, but if I were to sort of extend the head to be slightly larger, that is H plus delta, then I might have an observation in space. And that gives rise to a strategy of observing data in order to create this neighborhood set H. That is creating unique pairs that are separated by by H, right. So, what we do is, instead of taking our scanner strictly like a line, we basically take a a V-shaped angular tolerance, which allows me to look at scan for spatial lags in in a larger area. Of course, we can't make this too big, we can't make the scanner too big, because then we will be going in some other direction altogether. We don't want to do that. We just want some tolerance, so that when we go from to lag 2, we are not so strict, we are also able to sort of look for values at a angular tolerance. We are also able to, we also want to be able to look for values slightly further away from lag 2, which is the H that we are working with. So, this is H and this is H plus delta. Of course, we do not want this delta to be too big, it is small enough, it is a little tolerance in how far apart are we considering the lag H. Of course, the tolerance could also be on the negative side. I mean, at a smaller distance you might find a value and you are like, okay, fine, I am going to take it. Okay. So, we sort of instead of a strict line representation of a lag vector H, what we do is that we come up with a more envelope formulation of this lag vector. It is a lag envelope rather, which has angular tolerance and it has length tolerance in both positive and negative directions. Okay. So, having said that, let us apply this idea to our data set. Now, my irregular lattice is given at the top, and at the bottom from left to right I have 3 different representations of the lag vectors. The size of the lag vector is exactly the same. So, we can say H is fixed for all 3 directions, right. When I say 3, I basically am pointing to the 3 figures on the bottom half of this slide, right. What you see is that H is different due to its direction. In case of the first figure, we are looking at a north-south representation of a lag, spatial lag. In the second, it is a east-west, or rather west to east, whichever you prefer. And the third one, we are looking at a southeastern direction so far as the spatial lag representation is concerned. In the north-south, if indeed my lag vector was so sort of fixed to be from north to south, all the lag representations in blue should have been parallel to each other, which is not the case, right. Some of them indeed will look like to be going exactly in the north side direction, for example, the one that I have marked on your screen. But some of them will take advantage of a angular tolerance, because I did not find a head exactly in south. Let me just go slightly right in the direction and find one for myself, right. So, this search panel allows you to collect data with that kind of tolerance. It is also possible that some of these sticks from north to south are slightly larger or smaller than the exact value of fixed H that we started with. Okay. Similar is the case for the east-west direction. You do not have exactly parallel, you have these inclined H vector representations, which basically is taking advantage of the angular tolerance in our in our search for the spatial lags, or our scanning exercise for spatial lags, and the same for the third figure. So, you can stop here for a minute and just visualize how to go about scanning or searching for spatial lags when you are given an irregular lattice. Okay. Okay. On the next slide, what I have for you is what I am calling as the semi-variogram cloud. A semi-variogram cloud, first of all, I am saying is built on ArcGIS. So, interestingly, I am now also introducing a software on which these things are calculated. It can look rather intimidating that I have to go and scan all the different lags and then collect those pairs, and then I have to sort of then calculate the mean squared value, the difference squared values for each lag, and then sum them and take a mean, right. Well, the software will do it for you. Every data point that you see on this graph is representing a given lag vector h. For example, the one I have marked in blue represents a lag of about 0.3 units, right. So, h is 0.3. For this h, I had a z of s and a z of s minus s plus h, that is 0.3, let us say, right. It is an approximation, okay. Do not take it literally. I take them and I square them, and I am looking at a semi-variogram. So, I actually divide this value by 2, and that is the value that I observe here as gamma, which is around 4.5, into 10 to the power minus 2. Okay. So, this is my gamma h, which is given as zs minus zs plus 0.3 in the direction of interest. The direction is east west or west to east, right. You can see clearly, and I am able to sort of get this point. So, for this 0.3 units, you can see clearly that there are many pairs. Okay. There are many pairs of interest, right. So, I might not have been able to mark all of them, but all of these pairs collected together is my neighborhood set N H, the neighborhood set N 0.3, N with 0.3 in parentheses, right. So, a bag that collects all these values, right, a set collection of all unique pairs at h equals 0.3 is denoted as n of 0.3 or n of h equals 0.3, and the modulus of this n 0.3 is nothing but the count of such values. So, what will be the count of these values? Well, we simply count all the yellow crosses along the stick, that is h equals 0.3. Okay. So, this is a semi-variogram cloud. It is like a scatter plot of data, right. The very important thing that we see here is that till now we have, whenever we defined the experimental variogram or calculation of variogram, we kept h fixed. What we have done here is that we have variable h. Okay. When I talk about variable h, I am talking about a process where I am first collecting the unique sample pairs of data or data pairs which are separated by h. Okay. I am varying, I am keeping fixed h value, and but then I am varying h direction. Second, I can vary h value while I have fixed h direction. For all the permutations and combinations that I get for a given value of h on this semi-variogram cloud, I am only using the distance metric. So, I am plotting all the directions with h equals 0.3 on this vertical line that represents h equals 3. Okay. Now, so we have moved one step further. We have calculated 2 gamma h for all these unique h values, right. Let us just write this down so that it is absolutely clear in your head what we are up to here. Okay. And then we vary these h values. So, we create 2 gamma h 1, 2 gamma h 2, 2 gamma h 3, keep going. Let us say you have a total of capital M, h values for which you conduct this exercise. This is the set of all variogram, experimental variogram values at different spatial lags, right. Now, spatial lags, it will depend on what the domain size is, what the domain shape is, and so on and so forth, whether you are working with a regular lattice, you are working with an irregular lattice and what not. But the point is, now I have a more than one representation of 2 gamma h. H itself has an index j, right. J provides me an a representation of how many lag vectors am I collecting the data for. This is all going to be an analyst's choice. I can have very fine h, I can have very coarse h values that will determine how large the capital M value is. Once I have this set of different 2 gamma h values, what I am going to be able to do is I am going to be able to have h on the x axis 2 gamma h or gamma h, either the variogram, it does not matter, it is just a scaling by 2, by a multiple of 2, right. And then I am just going to put this one value. Remember, the cloud is different from 2 gamma h. 2 gamma h is a unique value. The cloud is a collection of all these zi minus zi plus h squared values. Okay. So, so then we will be able to sort of figure out what these values are at different values of h. Okay. All right. So, going back, we should be able to make a sense of what these things are. When I said gamma h equals this, just be careful, I am not, gamma h is not defined like this. Gamma h is a mean of all these unique values. So, I in fact should not have used the representation, it is gamma h. It is just a experimental cloud version of gamma h, right. It is not the exact definition of sample gamma h that we see on this slide or what we have studied. Okay. All right. So, moving forward, so we will take a digression now and we will ask a question, that is the variogram a resistant statistic? What is a resistant statistic? To sort of get a sense of a resistant statistic, we can recall the mean and a median of a distribution. So, we have seen earlier that the difference between the mean and median is a reflection of whether or not a given distribution of data have a symmetric PDF. Well, more than that, the more distant mean and median become, they are also a signal for outlier values, right. The mean value is pulled away by the outlier value in its direction, right. So, if I have a left skewed distribution where the outlier values are sort of towards the right of the distribution, what will happen is that the mean will sort of get pulled in the direction of the outlier, right, whereas the median is more resilient to it, right. To get an example, you can simply take the a sample of sequence of numbers from 1 to 10, calculate its mean and it calculates its median. Now, to this sequence add a number 100, again calculate its mean and calculate its median. You will see that the median remains resistant to this outlier value 100 or 1000 to this original sequence of 1 to 10, right, whereas the mean sort of runs in the direction of the outlier. Okay. That is why the difference between the mean and median, which provided us the U statistic, remember, in the exploratory data analysis, allowed us to sort of figure out, whether or not we should be worried about outlier values in a given sequence of data. So the variogram suffers from this issue of outlier values. To see this, just realize that if I have ZSI being 1, being value 10, and ZSI plus H being value 11, then the contribution to the variogram is exactly 1 unit, that is 10 minus 11 the whole squared, which is just 1. But instead, if in local, at the lag H of Si, I had observed a value, let us say 1000, then the contribution will become 990 squared, which is a huge contribution to the 2 gamma H value. This will pull 2 gamma H to a greater positive value, which is then a reflection of lower spatial dependence. So having an outlier value will, create this misjudgment of lower spatial dependence in the data. To see this, look at the bivariate scatter plot that we have seen many times during this course now. Now for the value which is, let us say, 11, the corresponding Zs plus H, or the value nearby, is close to 18, right. If I were to not remove this and calculate 2 gamma H at, location 11 with H1, it will be definitely pulled in, quite a bit by this difference of 7 between these values, right. If I include these, the data seem quite scattered and the correlation or the covariance in this data seem to be low. So the spatial dependence is sort of becoming weaker due to this, this spread that the outlier values are bringing to this scenario. If I were to exclude these values and only focus on the values, that are in the middle, then the correlation seems quite high, right. Things seem to be moving in a direction closer. And as I sort of keep on excluding the outlier values further, I will have a smaller core which will look, more and more spatially dependent. Okay. So variogram by itself is not a resistant statistic. It can lead to a misestimation of spatial dependence in the presence of outlier data values. That is why we conducted exploratory data analysis before we introduced the variogram, right. That is why it is very important to exclude the outlier values before you go on to conduct spatial prediction or conduct spatial regression, okay. Because in the presence of these outlier values, the covariance structure, the spatial covariance structure in your data is going to be messed up, and everything that will follow, no matter how sophisticated your analysis is, it will be a misestimation. Okay? All right. So there is a resistant version of the variogram which is not so popular. Well, it uses the modulus of the difference, which does not allow the penalty to be squared. It takes the penalty and square roots it, right, and then conducts some power adjustment, some normalizing factor adjustment, but it provides us a median analog of a resistant variogram, right. So Cressy and Hawkins provided this version of a resistant variogram in 1980, right. Okay. So this is just an understanding of, when we have the Zi, ZSI minus Zs the whole squared, values, which is the semi-variogram or the variogram cloud, by itself, including the outliers, you can see that the distribution is very highly skewed to the left, right. Whereas if I look at the representation which the resistance statistic is using, which is the square root of the modulus or absolute difference between these locally situated values, then the distribution seems much more tighter and perhaps closer to what we are used to. Okay. So that is the utility that we see, experimentally we can see that even with the groundwater data that is Uttar Pradesh data, that is a real world data set, we see the difference right away when it comes to measuring spatial dependence in the data. Okay. And very small, these small values will exhibit large spatial dependence, that is to be expected. It is groundwater data, how much will it change as we move through the space, right. It is a geographical structure right beneath our the ground, but it is not going to be like tubs or walls built together. It's a large tub over space, right. Okay. All right. So let's come back from the digression to this semi-variogram cloud and now sort of start to build the experimental variogram, which is taking the mean value at each h, h value, taking the mean of this cluster points at each h value. Okay, that will give us the 2 gamma h representation, right, as we understand it. So let's see how the experimental variogram looks like. Not a surprise, the experimental variogram is just a point at each h value, and the point is nothing but the mean of all these scatter plot points or the cloud points zs minus zs plus h squared. So you sum them, you divide it by the total number of such values at a given h, that gives you a 2 gamma h value, right. Now, we have understood a few characteristics of this experimental variogram. As a class exercise, what you can do is now take a 2-minute pause and locate the nugget, the range and the sill on this variogram. So, I will come back in 2 minutes, pause your video, come back in 2 minutes, and then I will explain where to locate the range, the sill and the nugget of these variogram. We studied these with the theoretical variogram, all these parameters are the properties of a variogram. Okay, welcome back. So, in order to locate the nugget, range and sill, we simply have to fall back on their definitions. What is a range? A range is a lag distance at which the variogram reaches the sill. Okay. Sill is the large scale variation in data. Remember, it's C0, right. So, it's the level of 2 gamma h value when when there is no correlation in the data. So, the sill is just the distance between the origin and the vertical distance to the no correlation point is the sill. This is the sigma squared, the C0, however you want to represent it. At the, so the point from the origin on the x axis, that the farther that we have to go to get to this point, that this sill is called as the range. The range represents the distance from any given location to which there is some spatial dependence in data. Beyond the range, there is no spatial dependence in data. That means, for our groundwater data set, the groundwater level at tail will provide no information about groundwater level at head, where the head lies farther away from the range value, which is the threshold value after which we have no spatial dependence, no information whatsoever in order to predict what to expect. Okay. The nugget is a micro scale variation. We know its notation, it's C0, right. On a theoretical variogram, the nugget is something that where we have C0, right. So, nugget is the 2 gamma h value when h approaches 0, right. So, this is 2 gamma h when h approaches 0. Clearly, and something that we have discussed earlier, that the data are usually, we are not able to collect data very close to 0. Like in this case, I need a data point which was at a location where I just moved out from from 0. So, I needed data points that were very close, right. So, I needed where would this 2 gamma h value be? Just right outside this point, location S0. So, I should be able to do it for all sample points, if not some. Now, we said that usually we do not have these understandings, or we can't realistically collect data. If we are digging a large enough sort of monitoring well for groundwater, we are doing it at a location, you will never see a well right besides it. It's nonsensical really, right? So, what we do is that we consider this C0 to be composed of a measurement error, and a white noise representation of it. So, it is really predicted from the data rather than being calculated or estimated directly. Okay. And SIL is just the large scale variation in data, something that we have discussed in detail now. Okay. I hope this makes your understanding of an experimental variogram very, very clear. I sincerely hope so. Okay. So, some couple of last sort of ending pointers in this lecture is that by looking at the variogram, we can we saw that we started with the bivariate scatter plot, which we called as the H scatter plot, and we said we can get a sense of the variogram value. I am now going to go back and close the loop, that is, we can start with the variogram and predict variogram plot, variogram graph, and predict how the covariogram or the H, the bivariate scatter plot, which is the H scatter plot, could look like, right. So, consider what we are looking at, on the left hand side. Let us say we collect our H, value here. Let us call this H tilde. At this H tilde, you have a large variogram value. So, the 2 gamma H or a gamma H, which is a semi variogram value, is quite large, right. At this level, we know there is no spatial dependence in the data, no or little spatial dependence in the data. Hence, the bivariate scatter plot will be scattered to a large extent around the 45-degree line. That is a representation that perhaps there is no correlation in these data at that H value. But what if we were to look at this at a different H, let us call it H star. Okay. At H star, what happens is the variogram value or the semi-variogram value is small. So, if the semi-variogram value is small, that means there is significant spatial correlation in these data. There is quite a bit of spatial contiguity, spatial dependence going on around this value H, right. At the distance H from any given location, I will have a healthy dependence. That healthy dependence will mean that the data will be scattered more tightly around the 45-degree line, right. Why? Because if all these data points in the H scatter plot were to be located on the 45-degree line, we have a correlation of 1, which is perfect correlation. That is the place where the value of if at any H star or H double star, the value of gamma H drops to 0, that is perfect correlation. I have never observed such a situation with real world data sets, but theoretically that is what it is, right. So, when we started this lecture, we said we can sort of look at the H bivariate scatter plot, which is coming from local stationarity idea, something that we have seen earlier, and start to predict what a variogram value could be, experimental variogram look like. Now, I am saying we can go the other way around too, which should make sense, right, which is intuitive. Finally, spatial contiguity, which is a smoothness in the data set. Overall, large scale spatial contiguity means how spatially dependent values are in their local proximity. Now, if we look at the first figure, it is a coarse image, right. I mean, it's an image. Let's say you pick a picture from your camera, you keep zooming, and you come to a very coarse pixelated understanding of the world. Whereas, you can have a smooth image, which is let's call this image 3, and from 1 to 3 we are moving from a coarse to a smooth image. The variograms on the left, provide us a very distinct understanding of these images. For a coarse image, there is a large nugget, right. For a smooth image, there is almost no nugget effect, right. So, when you calculate a variogram or estimate a variogram, given the shape of the variogram, for example, if we go back, if I have a variogram which looks like, which sort of bends down to this value, it seems like the data are going to be quite coarse from the example that we were looking at previously, right. And if you have a situation where the value will be small, the nugget effect is small, you are perhaps looking at a very smooth image. So, the visual and the graphical understanding that the variogram encapsulates is very clear from this slide. These data are coming from Perch and Dersch 2014, but they are very informative in the sense of what to expect of a visual image if you look at the variogram and vice versa. Okay. All right. So, this image now says that we are going to move from an experimental variogram, a calculation based variogram, to a variogram model. Now, a model, unlike these mean scatter plots of squared differences, is a smoother representation of the variogram itself. Why should we go from an experimental to a a modeled version of a variogram? Well, we should do that because look, for a given h value, we have infinitely many directions that we can pick if we were to really get serious about or literal about the experiment, how are we defining our lags, right. Even if I fix this h, I can just keep on changing it by delta, keep on doing it. It's probably going to be countably many times before I can even get all the unique lagged pairs of data for a given value of h. Imagine doing it for different values of h or distinct values of the lag vector h, that is the distance h, right. That is an ominous exercise. We do not want to be doing that. It is like spatial prediction. We cannot be sampling everything. If you were to sample a population, then what is the role of statistics? What we are doing is we are getting some representation of the variogram at let us say the north-south, east-west, south-east, northwest, and the northeast, southwest direction, and that is about it. We are going to then use it to generalize what is the variogram value at that given h, no matter what direction you move into, right. So, to be able to do that, we need to move to a model version of a variogram, and that is the next step that we will start to look at in the next lecture. We will do this, we will study modeling variogram models in the next lecture. Okay. So, that is about it for this lecture, for lecture 13. I hope this was enjoyable and knowledgeable for you. Thank you very much for your attention. See you next time.